Welcome. This time we will take a trip deep into the human body. We are in a healthy artery. As you can see, the blood cells move without any problem, but if on the way there are many obstacles. For example, there is a narrowing caused by a coronary disease. During the treatment of a vascular aneurysm or the patient had a heart attack. There are three basic types of stents, including classic metal BMS stents, otherwise known as metal stent grafts. Before implanting this type of stent, the blood vessels must first be widened using the so-called balloon hearts. DES impregnated stents are so-called vascular stents that release drugs. BVS bioresorbable stents, i.e. self-absorbing biodegradable stents. The stent is inserted through a blood vessel, radial arteries in the lower or upper limb, or through a femoral vessel. Let's move to the diseased vein for a moment. As you can see, there is a narrowing inside which impedes the blood flow. During the stent implantation procedure, angioplasty, a small balloon is used to properly position the tube. In this case, implantation of a stent may be helpful. Let's see how the procedure itself works. The presented diagram is a simplification of the entire operation. We will look at the procedure at a slower pace. For angioplasty, a long, thin tube, catheter, is put into a blood vessel and guided to the blocked coronary artery. The catheter has a tiny balloon at its tip. Once the catheter is in place, the balloon is inflated at the narrowed area of the heart artery. This presses the plaque or blood clot against the sides of the artery, making more room for blood flow. The stent model was designed in the Ansys space claim program. In our case, we will limit ourselves only to the section of the entire stent, and more precisely to 1/7 of the circumference. We can design the stent as a whole, but our analysis will use the cyclic symmetry tool to speed up the calculations. We will carry out two identical analyses using one material. It will be Nitinol with a different structure. The first structure will be an austenitic structure, the second will be a martensitic structure. After correctly defining cyclic symmetry, clicking on the mesh our eyes will see a complete model. Frictionless support and pressure are defined as follows. Now let's go to the analysis of the results. First, let's analyze the displacement of the model. In the first case, the largest displacement is 0.83 millimeters. And the stress is 402 MPa. We can also select the option of the maximum and minimum stress place. Let's bring the model a little closer to take a closer look at the stress. Now let's move on to strain in the analysis. The fatigue analysis tools are also used. The following option is selected life damage safety factor as biaxiality indication. Equipment alternating stress in the program. Fatigue sensitivity charts of the model damage function were also prepared in the program, and then for the life of the model. Now let's move on to the second analysis. The material will continue to be nitinol, this time with a martensitic structure. As we can see, the displacements are much larger than in the first analysis. Because they are 2.84 mm in the first analysis, they were only 0.83, and the stresses decreased to 282.9 megapascals. Let's check as follows. Maximum and minimum principal stress. Stress intensity. Normal stress. Shear stress. Similar to the first simulation, let's follow the results of the fatigue analysis. The final stage of our analysis will be the comparison of several simulation results obtained with the use of nitinol material with austenitic and martensitic structure. Thanks for watching.